Hello, everybody. Welcome to the Warren-Barnett Memorial Lecture, which is dedicated to previous alumni of the ISCE, Hayden Warren and Peter Barnett. As Doug said earlier, we're having to stand in for Helen Goddard, who unfortunately has had a couple of bouts of flu and now has rather serious tonsillitis, so wouldn't be a lot of use in talking to us today. Today we've got two presenters giving this lecture. One is Hanieh Motamedian, who is going to discuss sound masking in corporate and healthcare environments. I think that sums it up. And then that's followed by Sam Wise, who is going to be revisiting some of the forgotten factors in speech intelligibility. So I think without any further ado, if you could make a start, Hanieh.
I've been looking forward to this. So we're exposed to noise every day. Some noises we don't really think twice about, some we can't really avoid. It could be your neighbour leaving at the crack of dawn, the sound of the coffee machine in Costa, the conversation in front of you or behind you, and sometimes if you're lucky to be on the tube, it can be deafening as well. So some of those noises have things in common. The things in common are that they're avoidable, and you can have some element of control over them. So normally these talks are about the extreme lengths we go to achieve good STI and good intelligibility, delivering a message. I'm talking about doing the opposite for the benefit of our well-being. When I talk about the corporate environment, I'm talking about your office. Lots of us work in open plan offices. Depending on the age you are, you've probably never worked in, well, some people have probably never worked in their own closed office. So they would know that speech is the most distracting noise in the office. Other people talking, other people's conversations that maybe you don't really want to listen to or that you shouldn't be listening to. A lot of studies and research have taken place around the workplace environment and how our performance is affected by the noise around us. So one of the papers that I read was about cognitive performance and recall. So when you were tested in an open environment about the various cognitive tests that they performed, when speech was completely absent, the highest performance was recorded, and then as soon as speech was more intelligible, that's when the results dropped. When you look at the feedback from the open office environment, so I work with a lot of office fit-out companies, I work with consultants, architects, and everything they tell me points to the fact that noise is the most disturbing factor for people in the open plan environment. It's not the temperature, it's not the quality of the furniture, it's not whether they're working in daylight or not, it's nothing like that, it's just the noise. And it's not noise that is harmful per se, it's just noise that is distracting. So the open plan office was designed for teams where cross-communication was really important, so sales teams or creative teams, or if you're more cynical, it's just because it's cheaper. So this is one of the standards that I talk about every day. It's about the measurement of room acoustics, and it talks about the radius of distraction as well. So I've been told that I should include some calculations and graphs and clever stuff in this presentation, so this is it. So what this table is showing you is that the performance, the axis, vertical axis, shows you that there's no change in the cognitive performance of participants when the STI rating is 0. But as soon as you start getting good intelligibility in your office, the performance reduces. So noise in this office can be unanswered phones, which some people find quite stressful, other people's conversations. And there's no legislation in place to protect us against these kind of things. And this is just a guideline, it's not more than that, it's just best practice. So one of the things that they talk about in the ISO standard is the radius of distraction. So I'm sure some of you have seen this type of diagram before. This is an aerial view of an open plan office where the source of the sound, so the speaker, is in the centre of the dark blue circle. So in the darker blue circle, everyone else has a sort of high intelligibility of the speech that's happening. So they have it's harder for them to work, to concentrate, because as well as listening to their own voice in their head, their own thoughts, they're also listening to, I don't know, Sharon talking about her children or Keith talking about his weekend, whatever the topic of conversation might be. In the lighter blue area, there's lower intelligibility. So they are somewhat protected from the source of the sound in their office. So my talk is about sound masking and how sound masking can improve the acoustics of an office. So you could also look at this circle as an office with and without sound masking. So in an office with sound masking, the light blue area, the people are protected from the speech of the talker. So working out the radius of distraction in your own office is quite straightforward, using probably some of the equipment that a lot of you probably already have. This provides us with a scientific method to prove or disprove whether you have a good quality speech rating in your office or not. If you did want to do it yourself, it's really straightforward. These are just some extracts from the standard, which probably mean something to more of you than it does to me. So when I talk about sound masking, the concept, I'm often faced with incorrect assumptions about what it is, and trying to tell people that it's not a magic trick, basically. It's not going to stop sound completely. So this is the basic description of what the system is. And this table, this audio spectrum analysis, roughly is the frequencies that we try to emulate when we calibrate a sound masking system in any given office. The frequencies here are matching the human speech curve, so you have maximum efficacy in speech privacy with any given zone within a larger office. So going back to the radius of distraction, this is a rating that some people use, the speech privacy rating. This is an office without sound masking. And you can tell from the diagram that, in the same as the other blue diagram, there's a source in the centre of the office, and the people around them don't really have a very good speech privacy rating. So they can hear quite intelligibly what the source is saying. This is an office without sound masking. This is a real place. This is some genuine tests that were carried out. This is an office with sound masking. So you can see that the speech privacy rating is improved in those people that would be in the lighter blue circle. When I visit end user companies who have a very limited understanding of sound masking and what it can do for them, I talk to them about how sound masking is covering the sounds that are in the office. It's not really replacing them, cancelling them, dividing it invisibly from the rest of the office. The noises are still there. And this just shows a noise reading from any office. It's quite typical. And I show this to them. These are all the noises that you can hear in the day in your office. But with the addition of sound masking, a lot of those noises are covered by the sound from the sound masking system, which is much more pleasant, unobtrusive, and not noticeable if it's done correctly. So in this scenario, there's only a few noises that would actually be perceived by members of that office. A lot of the people that I speak to are very preoccupied. Maybe they have a negative understanding of sound masking which is not based on anything rational. They just think that it's going to be something that's annoying. Why? I don't understand, you're adding noise into my office to make it feel quieter. Can you explain that? It's quite counterintuitive. So one of the reasons that I one of the factors that contributes to a sound masking system being unnoticeable is when the sound masking level changes in line with the ambient noise of the particular room or zone. Now, for those of us that don't speak French, the red line is the ambient noise, and the blue line shows the sound masking system reacting to that. A lot of offices that I work with are concerned that the sound masking system is going to be ineffective when the office is loud and not effective enough when the office is quiet, or it's going to be annoying when it's quiet because people are going to notice it more. So some offices turn it off when it's quiet, and then the next people who come in when it's louder, they forget to turn it on, so you end up having spent a lot of money on a system which isn't really being used. This is one more standard that is quite new to the UK. It's come over from America, and this is a standard that I'm sure some of you know about already. But where we usually focus on the sustainability and green rating of a building, the Well Building Institute has come up with a standard where we focus more on the people in the building. So it looks at air quality, water quality, companies who are well certified. There are different standards. If you're certified, you provide a certain amount of nourishment to your staff, fruit, vegetables, smoothies in the morning, yoga on the terrace, things that are supposed to improve your happiness every day, because, you know, I think we sometimes forget that the biggest expense of a company is the people, and people are expensive to replace. So I mainly work on the corporate side with sound masking, but there is a general shift towards more well-being in offices, and this is something that has been a shift over time, but I think it's becoming more and more prevalent. So this is my second study area, which is really interesting, sometimes more than the corporate environment as well. So a lot of research has gone into noise in our hospital environment. Noise in an ICU ward in particular impacts on the ability of patients to sleep. It impacts on the practice staff and affects family members too. If you're visiting people, you know, everybody's been to hospital, visited someone in hospital. It's not necessarily a pleasant environment. So this picture is of a workshop that was organised, and we ran a pilot experiment to test different soundscapes, including sound masking, in a hospital environment. The workshop participants were social scientists, artists, doctors, clinicians and service users, and me and Stan, industry partners. The experiment sought to gather qualitative and quantitative data on people's perceptions of soundscapes in the hospital environment. Sound masking wasn't the only product that we looked at. We looked at noise cancelling headphones and also sleep headphones, the one that kind of just sit flush to your ears and you can sleep quite easily in them. When we listened to the hospital soundscape, which was played through the loudspeakers in the simulation ward where we did the workshop, the majority view was that it was awful. It's loud, it's obtrusive, it's alarming. These are some of the comments from nurses and doctors, transplant patients who have spent a lot of time in hospital, and also family members who had also participated in the workshop. This is in an ICU ward as a sample. So we will accept that there's a lot of noises going on in hospital wards. There's beeping to make sure you're alive. There's beeping to make sure that the equipment keeping you alive is alive. Some noises are louder than others. Some people are louder than others. But one of the participants of the show was working towards her PhD, and she spent 1 year recording everything that happened in a particular ICU. And every week she went through all of it, and every occurrence of noise, she attributed it to a particular category. And communication was 40%. So I thought that was quite surprising when you think about it. So during the experiment, we played sound masking and sometimes overlaid it with nature sounds. Rainfall was a favourite. And these are some of the comments that we got back. And these soundscapes were played over the ICU noise, so they're not replacing it. So, sound masking is used in the corporate environment to improve productivity, increase well-being, to increase speech privacy and reduce distractions. These are all really good things that are really useful in the open plan office. The research suggests that certain soundscapes can not only be pleasant but also restorative, which is really key, particularly in a healthcare environment. The speech privacy standard that I talk about, the ISO standard, is more commonly associated with corporate environments. But actually, if we mirror that standard into a healthcare environment, the speech privacy, it would make a hell of a lot of difference. We always... oh, nobody liked the bird song, I forgot that bit. People found it disturbing because they were indoors, but hearing the bird song made them really question, am I indoors, am I outdoors? And some of the transplant patients that we worked with had spent a hell of a long time in hospital, and one of the problems that some of them suffered was delirium. So when you don't know what on earth is going on, hearing birdsong, you can imagine your imagination takes you places. One of the ex-patients, she suffered delirium, unfortunately, and she had a nightmare. What she thought was a nightmare was that she was in a foreign country. She didn't know where she was. But then when she recovered from that, when it was spotted, she noticed that some of the nurses were actually speaking their own language in her ward, which was disturbing for her. But you wouldn't have thought twice about nurses speaking their own language together, but for her that was really disturbing and led to some nasty nightmares during her recovery. So another issue it raised was education of the staff. Some noises happen in hospitals that are quite unnecessary, or the same noises in an adult ward happen 24 hours a day, but for some reason the same activities in a baby's ward or child ward, the nurses take more care to be quiet at night time. That's what the research found. Even though everybody's sleeping, whether they're adult or a child, for some reason we are quieter, behave more quietly when we're in a children's ward. There's no real reason for that, but until someone points it out, you don't really notice. So we always tell our friends, whenever they've suffered a trauma, physical or mental, take it easy, relax, you'll recover more quickly. So I think we should afford people in hospitals the same by improving their acoustic environment, because it's a challenging place to be. So coming back to my original question about who cares about noise, we all should. That's it.
Thank you very much, Hanieh. If you like to sit to one side, if we have Sam Wise next, please, and then we'll take any questions at the end. And I remind you that at the end, we'd like you to head over to the exhibition for your free lunch and coffee, which will be around 12:15. Thanks very much. That's great.
Good morning, everyone. It's a pleasure to see you again this year. Having had a number of years of absence, I came last year and enjoyed myself a lot, and then I was invited to do this little talk. Just to say that this is really a revisited talk, and I do apologize for the fact that over those years when I haven't been here, I have no idea of how much of this material you may have covered. But what I will be trying to do is taking a little bit of a different tack on it. It's one thing to have to try and calculate and pre-verify a specific acoustic performance, whatever that performance, and it's no easier when you're trying to specify a sound system to achieve a specific STI or Alcons or whatever it may be. On the other hand, there are many, many ways in which we can develop our skills to learn how to make a better system than might have otherwise been done. When you're reaching that limit, you need people who are really genius at even using the electronic modeling systems and interpreting those results. But to improve how your sound system, your options that you can have in any given location, is a case of learning about human perception. And today we've learned about human perception regarding the behavior of crowds, of people in crowds, emergency crowds. We've heard from Hanieh about the use of sound masking. Sound is all about people, and it's all about how we receive that information content, decode it, and make sense out of it, if that's what we wish to do. Or in the case of irritating people talking about their holidays next to us, or worse, and we're trying to not pay attention to it. So this is really partly what I would call, what I would like, if I give you anything, it will be this. How to get the design principles in your belly so that you make a lot of very right judgments about your design criteria when you're meeting architects and others, and you're trying to get this system going in the right direction long before you're doing any models or anything else. That's really what it's about. Okay, so we have the Alcons equation. Oh, and by the way, this is revisited. So the slides in here, some of these are from presentations I gave 20 years ago, and the tools I used then were also 20 years old, but I have to tell you, the fundamental things underneath have not changed at all. So we have these ways of measuring and ways of calculating, and there are other ways now that are kind of in the pipeline or are actuated of new softwares. And then we have people like Peter Barnett. Some of the things I have in here, Peter Barnett managed to drag them into his spreadsheets, I suspect. They were always a secret, so we never got to see them. But reading between the lines, I think some of what we see here that's missing from these calculation methods, he knew them, and he actually could account for them. I have no idea what Peter Mapp has used over those same years. Okay, so we have this equation. We think, oh, equations. I know many of you will not like them very much. On the other hand, this equation is useful because there are some ratios and things in here. We can learn about them. We can go out and we can listen to a sound system, and we can look at, for example, take this sound system up here, the one that's built in. We can look at things like how far away are the loudspeakers. How many loudspeakers are going to be hitting me? Right? This is what this equation is about. What is the ratio of useful energy? What area of that energy coming out of those loudspeakers is covering me, and what area is spewing all over the room and creating reverberation? This is the kind of thing we need to look and learn about these equations, not to memorize the equation, not to even use it to do a calculation, but rather to use it as a tool to begin to understand things that we are seeing with our eyes, hearing with our ears, and wanting to apply in our day-to-day life. That's my opinion. To get this equation into a belly understanding. Okay, so we can keep going about this, right? There are various things that are assumed by this, and there are various things that are ill-defined. And so when you're trying to nail the real number, which might be required by standard, it's one thing. But when you're trying to use the belly knowledge, it's something else. Okay, so then we have our RASTI, our modulation transfer function. Oh, thank you. Thank you for bringing this. There we go, we'll calibrate it in. It's a red one. Is there a red one? No, there's a green one. Okay. There's a red one as well. Oh, and there's a red one. I can't see the red one. Okay, the green one. So in modulation transfer function, there is the perfect audio that we want to take from place to place. And here is it when it's corrupted, and we fill up these gaps between there, okay? That's useful to know. So what I'm trying to look at, Hanieh was using this filling up in between to avoid understanding, therefore avoid distraction and irritation. We want to prevent that corruption in between because we want to improve and maximize that clarity and acceptance of the information, the ability to decode it. Okay, but except for perhaps Peter Mapp and Peter Barnett and Helen, and there may be a few others, there are some things in this which are not well defined, not accounted for, and you have to begin to think about them. What are the numbers which cause the filling up that's irritating or harmful? What is late direct sound? Okay? So I'll get to some of this in a minute. Anyway, I'll just skip over this. And then the other thing that didn't happen here, and we get to it a little bit with the emergencies in stadia sort of issue, where the background noise is so loud, many of you would have also been musicians. And the situation where you have the sound system turned up so loud that two things happen. The one thing is that the lower frequencies mask over and cover up the higher frequencies, and therefore take away the very thing you want to hear when you turn it up. The same thing happens, of course, when you get in a reverberant room. The mix engineer is not too good. First thing he does is push the faders up, push the faders up, push the faders up, and it all gets worse. But at the same time, our way of hearing is also getting worse. So it's not only a masking thing, we're actually reaching the limits of the ability of the things inside our ears to actually flap around in a helpful way. They're starting to flap in an unhelpful way, and therefore we cannot get improvement in intelligibility through turning things up. So we're talking about these speech curves. So Hanieh was working around in this area, but here are the slopes. They aren't the real slopes, I don't think, because I realized my own information was somewhat lacking here about these masking slopes. But here we have an octave level, band level, so something like the level here. And here we have the slope of the curve, but the slope of masking doesn't tell me whether that's 10 dBs per octave or 10 dBs per decade, and I didn't have a chance to go back and check it. But basically, when you turn this up by talking louder, like I can, even without a microphone, then you're causing masking of your high frequencies if you're not careful. But if you turn this thing up, you're also doing the same. If you notice, the high frequencies are nearly as low as that one. But the slope, this orange line here, is the fact that the masking gets worse. It covers up further up the louder you get. So those are things you can learn, and you can try to use them and apply them and speak to clients and try to explain to them why just turning the sound up isn't going to work, and why we must have an alarm tone, and we have to try to get the crowd sometimes to quieten down, and why in reverberant spaces we get mix engineers who just don't get it. Okay, here's Peter Mapp, please stand up. The most important book you can own as a designer is The Audio Systems Designer from Clark Technique. How old is that now originally? 30 years now? 1985. I have a copy. I have a copy of this with A5 in an A5 binder, and I've added a few pages which you can license from me, Peter, should you wish, over the years to help me, but most of what you need was in there. And this is a very, very useful graph about speech intelligibility. And this is where I'm going to get to a key element of my talk. And that is about what I'm calling, I'll explain a little bit more in a minute, lateral versus vertical sound systems, and how this plays into this graph. But here's a case where you can have this graph and you can look at it and you think, okay, it's a graph. I'm not going to memorize that and the colors and everything about it. But critical things, 35 milliseconds, critical time. At that point, you can call it a tripping point whereby your speech intelligibility starts to decline if energy is arriving from somewhere else than where you want it from. So if these loudspeakers aren't good enough and the room's too lively, then you get, or up here, we're going to talk about this one in a minute, because this is a kind of almost overhead system up here. This is a tripping point. It's not audible as an echo. Over here, it becomes audible as an echo. And this level transition is important. As you can see, when over here, you can afford for the delayed signals to be louder than the original signal. Because if that's the original signal at 0, the delayed signals coming from elsewhere, like reflections off the floor, which add up for you sometimes, you'll see in a minute, can be louder, and it still helps. But over here, it starts to cause a problem. So it's a useful thing to have this book, because you can go out, you can visit a place, and you can think, why was it like that? And I don't know whether you all do it. Sorry, I guess I'm on this mic, not this mic. I don't know whether you all do it, but one of the things I learned to do from very young was, if I'm going to be involved in sound and acoustics, it's because I love sound. And if I love sound, then this is even before you had these things in your pocket, phones, and you were wearing things on your head all the time. Sound is all around us. And when I go into somewhere that's a public building or a PA system like this one, I try to get a grip on why it's working, why it isn't working, where is it, what's going on, what are the room finishes and everything else, to teach myself this belly knowledge about what is good and what is bad. And then I go back and I open up Peter's book and I see, yes, there's a relationship there. I never really understood it before. So I'm closing the loop between theory and practice and experience. And that builds up my knowledge really well. So it's something I highly recommend, and I'm sure a lot of you do it.
Sounds like you take CPD, continual professional development.
Yes, yes, and you have to give yourself you have to give yourself a CPD. If you do this all the time, you get to give yourself a certificate. And if I ask you the right question, you give me the right answers, I'll make sure you get the certificate so you can get your pay rise next time. So I'm cheap. For that service, it's only £2.50 an hour, because I would love to hear about those, yeah? Okay, so anyway, the early sound, so let's try to get some definitions. This is the early sound, this is the later sound. The late direct sound, okay. So we'll see some in a minute, but up there is a loudspeaker. And we notice it's 35 milliseconds. So 35 milliseconds, how far is that?
35 feet.
35 feet. How many meters is it? 10. All right. So I'm going to move over here. And where am I with respect to that loudspeaker over there? 35 milliseconds? At least, yeah? So that one is going to cause me a problem. And the further I get over here, out of sight of that one, so that one's leaking some sound down on me not very well. That one over there is going to be louder. It's going to be shit here. Not going to be very good right here. So this is, like I said, is a practical application. That's late direct sound. That loudspeaker is pointing straight at me, and I'm getting that, even though it's harmful.
But Sam, if you read the graph, it actually says it helps it as long as it's lower in level.
But over there it isn't, and I can show you in a minute. Or it may not be lower in level, because I agree with you, Peter. And we'll see an example, and we'll listen to an oralization. If I'm off axis of that, so I'm not getting the high frequencies, as I was standing over there, I think, that one could be louder, and I'm in this red zone. Okay, that was my point. And if you look and you listen to get that belly knowledge, you're out in some place, and I think I've got a picture in a minute. I'll show you one that taught me this lesson very well. Then you will start to really take on some of the equations and graphs and other things, and as you take them on, you'll begin to apply them to other, and your whole quality of your work and your advice will go up. That's all I'm saying. So that those of you who are long in the tooth like me have probably learned a lot of this. If you're a bit younger, it's great fun. That's all I can say. Okay, so echo is late discrete sounds that are coming really from over here. Reverberant sound is just decaying general reflections around the room. Okay, and then this is this graph kind of superimposed on an old ETC from an old piece of ease software. And so here are a bunch of arrivals. Here's the accumulative energy from those arrivals. And there is that disturbance threshold overlaid. And these here are causing destructive contributions to that audio. Okay? And so we'll see this graph in various forms. This is a very dense thing, so it will sound like a reverberation. All right, so then this is partly about overhead versus lateral. In the underground, when I first gave this paper, we had lots of lateral sound systems, and it was absolutely diabolically terrible. The shock that came to me, the reason why I'm giving this particular talk, so I beg your pardon if it's the same as what you've heard for the last 5 years, 10 years, was that I've seen university reports from university departments as part of master's research projects condemning the present design of the underground's communication systems, which are 400–500% better than they were when we had lateral sound. And they were recommending going back to the old way, which didn't work. So this put fear at me, and I thought it's time to go back to some old slides and talk to them, even at the risk of boring a few old codgers like me. But let's go on with it. So what is an overhead system? Well, I say it's strongly downward. The direction of the sound toward the listener is strongly downward. I didn't make an angle there, but I do generally use a rule of thumb of 45 degrees. That one and that one, when I'm in the middle, are about 45 degrees. And so when I'm over here, that's kind of an overhead system, but when I'm off to the side, it's becoming more of a lateral system. And thus, when I'm in the corner over there, out of that one's direct sound field, then I'm going to get the problems I get from a lateral sound system. This sound reinforcement I'm having here is a lateral sound system, but it's not causing a problem. And that is because the levels, horizontal dispersion of those loudspeakers, and the distance between them is okay for this room. And so it works for us. So it's not to condemn any lateral sound system. But if we look at an overhead sound system, when I first joined Arup, I was repeatedly told that sound system you've just designed will not work. And then when commissioning time came and my boss came to walk through the building and look at his concert hall acoustics, and he heard an announcement on my room, and it worked. He said, this shouldn't work. Okay, he never actually learned why, because he didn't really want to talk about anything like that. But here, in the middle, so I've got 3 listeners here. There's one off to the side, like I was standing over there. And that one off to the side has no direct sound. Sure, at some frequencies they're getting some. It's getting a little bit of off-axis sound there, and it's getting a wall reflection. And of course, like here, he will be getting a floor reflection. So he's not on the axis, he's not within the loudspeaker beam, but he's getting useful adding up. This guy in the middle gets something directly from that loudspeaker above. He's getting some side, lower frequencies probably, coming to him from the side, and he's getting a reflection from the floor there coming up. All helpful. This guy's between two loudspeakers, and he's getting contributions from there and there, where he's within the coverage just, and he's getting a bounce off the floor, both sides, and if he was getting something from the wall, all useful. So with an overhead sound system, what you find out, number one, is that more of the early arrivals have a higher likelihood of being useful than they are with a lateral system. Okay, then horizontal lateral system. Okay, so this one, if it was lower down, would certainly be a lateral system with a speaker there, a speaker there, a speaker there, and a speaker there. Yep.
We're just getting short of time.
Are we? Okay. So I'll move. What time are we finishing?
In 3 minutes.
Oh, I thought we had an hour overall.
12:15, I was told.
Okay, that's all right. All right. So I will skip through, and we will skip through some stuff, but there's tradition in that, and some of the people who follow that tradition are here in the room. Anyway, so there's arrivals, and you can see just like what I'm describing, I'm in the middle, I'll get a very strong, equal, balanced contribution, but people to the side may not. Okay. Here's a picture from Waterloo Station, and this was in the midst of a changeover, which happened about 2000, I think. And so we have this, which is more like an overhead system, and this right beside something's more like a lateral system. And of course, these were designed to be longer throw than that. And it was fascinating because you could walk behind these buildings, and you see there's some of the sound system up there, and you could hear the difference between the two systems. The horizontal, the old system was still running at this moment. These were just being installed, and you could go behind the building and block off some of these signals, and then later on you came back a month later, and that was turned off, and these were turned on, and you could compare the two of them. And this is what I mean about looking and listening. So it was a very good opportunity to listen to different systems. And this is more like what is now on station platforms and the underground. And in the underground, it typically points straight down toward the join between the platform and the tracks, and so the reflected sound gets bounced off the cars, or it goes down and gets caught and reflected down inside the tech recess, and it works very well. Okay, I won't go into this. This is all about loudspeaker directivity, and that can make a difference. So here is about a conventional loudspeaker, and it's some reflections from it as an overhead system. And then here's a sound advanced speaker. This is old technology. I wish they still made them. And the differences, but you can see here, this is falling down, and that's 30 milliseconds, 35, and we're down by about 20 dB, so we're inside of the curve, and it mostly is good. Okay, I won't do this. We've all proved there were some great tools which were available. EV Array showed you what happens so much about comb filtering, the loudspeakers being near walls, and you could also see how different devices, you could mock up a reflection from a wall at very low frequencies and see how the lobes would generate. That was so quick to use to gauge things or to tell a client a story. Okay. Right, so here we have Gatwick, one of the two terminals, the airside area. And the original system was around the edge there, and I'll play that for you in a minute. And there is the new proposed system, which was a lot less loudspeakers within architectural formations overhead. Okay, it was very hard with glass roof, lots of noise, and architects didn't want to see any loudspeakers, and they never do. It's a big space. It's 32 meters that way and 25 meters that way. So, and the RASTI was very good right in the middle, where you had all those loudspeakers around the edge pointing straight at you, and around this outer third, it was absolutely terrible. Okay, and there were amplifier failures, and the automatic gain adjustment was going in too big a steps and a number of other things. And here's the ETC for that one. So you can see 69, 70 milliseconds later, the levels hardly dropped. So we'll go and listen to that one in a minute. And there you can see the disturbance curve, of course, is a little bit of a curve, but this line tells us that these are above. It's a good approximation, that line to the curve. Okay, and so we put in this overhead system, we trialed some things, and then this is what we got in our model. And what we can do is just dump down here and finish with some playbacks of, I'll pick a couple of the worst ones. So the original system, this one here.
Monetary systems have evolved to make use of this base 10 notation. France became the first decimal country in Europe in 1799, joined by Belgium, Italy and Switzerland in 1865.
Okay, bear in mind that there's no reverberation in that. It did sound like it had some, but it's all this early sound stuff we're talking about. So there's no real, it's worse than that. And it's also background noise, much worse. We're going to compare that in a minute to the other.
Monetary systems have evolved to make use of this base 10 notation. France became the first decimal country in Europe in 1799, joined by Belgium, Italy and Switzerland in 1865.
This is a good one to bring if you're giving a talk during Brexit discussions.
Monetary systems have evolved to make use of this base 10 notation. France became the first decimal country in Europe in 1799, joined by Belgium, Italy and Switzerland in 1865.
So the first one I played you was that one. I didn't realize you couldn't see my cursor. The second one was that one, and the third one was this one. And this one, of course, you don't hear the reverberation, although it is actually the same, because of those two, what sounds like reverberation is late direct sound. Okay? And then the revised system measured at approximately the same, or modeled at approximately the same positions.
Monetary systems have evolved to make use of this base 10 notation. France became the first decimal country in Europe in 1799, joined by Belgium, Italy and Switzerland in 1865.
And I will stop there, but that is that one. And I think you can all appreciate that was a very significant improvement by moving to an overhead system, even where it broke my rule, which is, my rule is overhead, if you've got great scattering up there, or you have a soft ceiling, or you have a carpet, or you have a bunch of chairs, any of those, an overhead system will almost always work. Whereas lateral systems can be useful, like this one, but you've really got to be careful and thoughtful in their use to be sure you don't get arrivals coming. The final thing I was going to say is that there's another factor here that I think is important. I've never seen it proved scientifically except about our human response. And we'd love to talk to the guy, Chris, was it, earlier? And that is that lateral systems, I think in general, they pick up on our information, our flight or fight, or what the hell is it, where is it? When it's down low, that takes away from our mental decoding that we are applying to taking the message out of this acoustic flapping that's going on in the air. And when we're overhead, that's missing. And in exactly the same, if you went in with any kind of metering system to measure intelligibility, you would not measure any difference. If you put two systems in where you could not measure any difference, you would, on your PB word scores, you would pick up far more from an overhead system because this distraction isn't there. And I think Peter Mapp knew this very well, and I believe that Helen knows it because she has all the history there. And so it's one of the things to think about. That's it. Thank you very much.
Thank you. We've run over slightly, but if there's a couple of questions anybody wants to put, yes?
Yeah, I just wanted to ask Hanieh a question.
Great.
It's a really interesting presentation, thanks. I can also vouch on your healthcare acoustic study because I was actually part of it, and you made great strides to investigate the benefits of sound masking in that environment. So I can certainly extend my interest in that particular study. But my question was actually about the first part of your presentation, about the office environments. And you mentioned the ISO 3382 Part 3 information, particularly with the D2S metric that you can measure in a building on site. Are you aware of, or do you think it would be useful to develop any studies to demonstrate how that radius reduces with the sound masking active and when it's not active, and show that to users of the system so that they can get a tangible understanding of how that distraction area reduces with the use of the system?
Yeah, I mean, I don't really pull out the standard when I go into the end users, but the standard offers a more scientific method of the calculation of the radius of distraction, which is something that you can apply to all offices. But the speech privacy index tables, you know, with the different greens and reds, that one's actually a proper test of an office, the same office with and without sound masking. So although the speech privacy index is slightly different to the radius of distraction, there's parallels that are easy to demonstrate. But yeah, everybody wants it proved to them, which is quite difficult to do. But the best we can do is offer research and case studies.
Okay. Is there a question for Sam? Anybody? No questions for Sam. Okay, thank you very much. And if you could make your way through